I'm Mike here. I'm from Wolfram Research Technology Group, and yeah, so today I want to talk about introduction to graph neural network and what we can do in Wolfram Research. I mean, Wolfram Language. So yeah, this is my personal interest. So I try to explore it. I mean, in this month, but unfortunately, I don't have enough time. Yeah, but let's go on and see what can we do. And yeah, first let me give the overview of an introduction. Can you hear me? So introduction to graph neural net. That's presentation mode. And yes, so as we know, in these years also there's a popular application. I mean, exploring in graph neural net, and it will be okay. Depends on the task. So you will complete the node. The node will be related to the spam detection and fake news and some physical simulation. Also for edge, so to predict the relationships between the nodes or the target you're interested in. So it will be recommended system and traffic prediction, and also other application of predict the graph itself. And yeah, so let's keep going on. So let me give a quick overview of graph data. So graph, as we know, it composed by the node and edges. Edge define the relationship between the nodes. And as you can see, so the graph looks like here. And usually each node maybe have some attributes. Also, sometimes edge maybe have weight or some additional labels. And for some purpose, there's also the global attribute for the whole net. So here's different conditions. So yeah, and in graph neural net, so this attribute will be helpful for the as initial input, and will help GraphNet to learn the appropriate embedding in the end. So okay, we start from attribute of a node, and then after graph neural net, we want to generate appropriate embedding to represent the property of each node. And here's another example of graph data. So image, as we know, image is really image investigation in deep learning is quite exploring well. So, but actually the image can be considered a graph, can be decomposed in graph structure. So if you think of the grid structure of image and the channel intensities, then the grid first part of structure can be considered graph itself, and the second part can be considered as the attributes of the nodes. And similarly, like in transformer, so they try to use the order, consider order or position embedding to mark the position of each word. And of course, each word has its own vocabulary embedding. So yeah, I just want to show, okay, everything can be decomposed into the graph structure and the attributes. And here the sentences similarly. So let's go next. So, okay, so let me introduce the simplest representation of graph. So as we know, the graph have different types. So the left part is a direction graph and right part is on direction graph. So the easy way to represent this is to use the adjacency matrix. So like, for example, there are 4 nodes, and we can use each node as row and column of matrix. And if the 1 and 4, if the nodes are connected, there will be number 1 here. And because it's on direction, so this symmetric adjacency matrix, and you can export it. And also the matrix, the link between or the edge can be weighted. So the adjacency matrix will not only limit to 0 and 1. And so if there's other, for the big data set, you need some sparse representation. So yeah. Yeah. So in graph neural net, so we need adjacency matrix. So usually we represent by n matrix like this. And also for the attributes or the features of the nodes, we assume the dimension will be, the feature space will be F, and the total features of the nodes will be dimension n times F. So we can do some operation with input X, and based on the graph adjacency matrix here. Okay. So yeah, before go on the graph neural net, so let me just remind you some principle notation or ideas for graph. So as we know, we have adjacency matrix n by n. And first thing, we have degree matrix. So just sum over row or columns. And once we have degree matrix, we can define the graph Laplacian. And the graph Laplacian will define the property of the graph. Like if you check eigenvalue, you can check the zeros eigenvalue, determine the connectivities. And yeah, let me skip this. And also, so in graph neural net, we need additional normalized Laplacian, which will deal with the gradients problems in the neural net. It's similar to idea to the convolution in images. So yeah, we want to normalize so such that the information can propagate longer. So just remember we define the normalized Laplacian like this. And also we have another normalized Laplacian. So you can consider the adjacency matrix add by self loop. So originally, so the graph don't have self loop, but for operational convenience, we add self loop, and also we normalize it. Yeah. Any question? Okay, let's keep going. And here is the basic operation for graph neural net. So suppose we have graph input. So we will separate the graph structure we call Laplacian or adjacency matrix from the attribute. So yeah, and we go through the general blocks and we update the attribute, or we generate the embedding. We learn the embedding for each node or for each edge, even for the global representation of the graph. And eventually we do classification. Yeah. And so you can see, okay, there are 3 types of the text. So yeah, the first one is classification of nodes, and the second and third is the classification of whole graph and edges. For the graph classification, we can say it's like image classification. So we need to supervise it. So it's inductive. And for the node classification, is like image segmentation, and is semi-supervised. So we focus on the same net structure and some nodes as training point and other part as the test point. So we want to predict the rest of the point of the net. Yeah. So if you have different net, you have to train train it again from the beginning. Yeah. And also the age levels, then kind of relationship prediction. Yeah. So yeah, in this lecture, I try to construct the node classification in Wolfram language because I don't have much time. Maybe next time we'll try to explore the graph classification, but now I will focus on the node classification. Yeah, let's keep going. So yeah, first thing is okay for the graph convolution. I mean, for the graph neural net, first thing we'll think about how to apply the convolution to the graph. So think about this. So for the image, when we do convolution, we try to update the pixel we want based on the neighborhoods. So similar ideas, we want to use based on given graph structure, we update the nodes now based on its neighborhood. So then we need the adjacency matrix. So you can expect during the graph neural net training, the graph structure is fixed, but the attribute will be changed based on the structure of graph and also the trainable parameters. So you can think of okay, the previous layer will be before the update, and after the update is the next layers, and so on and so forth. Okay, so far so good. Yes, so that's why we need adjacency matrix. So let me, I will show you example later. So just yeah, it's based on the probability of adjacency matrices or Laplacian. So and yeah, so because time's limit, let's keep going. And so the key point here is okay. So yeah, so as you know, for the image convolution, we use because the filter convolution will preserve the translation symmetry, and the graph there's no orientation, no specific orientation. So we need to do some operation in which you can preserve the permutation symmetry of neighborhood. Yeah. So just remind you. So that's why they suggest the message passing, like the idea here. So you do some adjacency operation, adjacency matrix operation, and pass to the information to the next neighbor. So we call it one hopping. And yes, so just I mentioned before. So after that, we update the embedding space by one hopping or by one layer operation, and eventually the goal is to learn appropriate embedding of each attribute, like for vertex or edge or global. And sometimes for as a node, so the global because yeah, it's similar to image. So if you do more layers, you perception field will be larger, so you can catch some global effect. So, but for the network is graph also have similar issue. So because the net is too big, so you cannot explore whole net at once. So the topology will be different. Yeah. So and then the global embedding will be helpful. I mean, to help the node to touch each other faster, so to get better information. But I will not implement this in this talk, but yeah, let's keep going. And yes, so the message, the information or the embedding information can pass not only limited to node, you can pass between the um, from the vertex to edge or edge to vertex or the globals. Okay, let me go faster and because okay, we'll see some results. Yes, so let's go to the topic of the convolution. So the graph convolution, the simplest simplest implement of graph neural net is graph convolution. So and this is simplest type you can have. So assume you have just mentioned the normalized Laplacian, and because we know the dimension of the attribute, and once we tie this is just equivalently to hopping to the nearest neighbor. So if you know the matrix operation, so yeah, then the W here is the matrix try to convert the input into appropriate dimension or embedding. So that's the simplest part of graph neural net convolution. Any question on this? So the key point is because the as I'm remind as we know the dimension of X is n times f, and this dimension n times n. So you can think of adjacency matrix here, and this just do one hopping of the attributes. So after one operation, your information propagate once to the neighbor. And here are some basket metrics or adjacency metrics or Laplacian we will need in the following experiments. So yeah, just remind you. So these are normalized and additional normalized one. Yes, and yes. So this is about the idea of graph convolution. And in the end, we will use the nonlinear like sigmoid or the nonlinear function like ReLU, something like this. Yeah. So yeah, that's the principal ideas. And so because we don't have much time, so let me skip the code. But you can see easily. So here, so the Python operation, so it's quite easier. So you have once you have Laplacian and your input will times the linear operation W. Here's the W, and then do another multiplication and take as output. So let me skip this. Okay, so because this is more complicated, but the idea is this is so-called the spectrum operation. So it's kind of a global effect. Once you have Laplacian or adjacency matrix, we can diagonalize it. The diagonalization is linear combination between the nodes, right? So that's a global effect. So this kind of convolution will be act as the global convolution, but in practice it's difficult. So that's why we use this expansion. And yes, my goal today is try to demonstrate how to implement the graph convolution and this expansion in Wolfram language. And let's skip the math details. So, and let me just go to the notebook. Yes. So so basically, I follow the state exchange link here, and do some exploration. And so first thing I save the data in .dat, so and exploit it in Wolfram language. First thing is, okay, we get the data and do the metrics I just mentioned before. So like so these asymmetric normalized adjacency matrix, and we have degree matrix, and also we have Laplacian, and this is for expansion purpose. And yes, so this is a rescale Laplacian, so on and so forth. And this is if you cannot remember so many, so you just keep mind in this list for graph convolution. Yeah. So we add the adjacency matrix is added by cell group and normalized by the degree matrix. And next we construct the net. Wait, maybe I need to run this. So okay, let me run the net and show the structure. So yeah, so here I just use 2 layers, and each layer construct in this way. So you can see there's a adjacency matrix, and the input will be the attribute or the previous embedding layers, and we do the linear transformation and multiply the adjacency matrix to 1 hopping, and then we do activation for the next layers. Yeah. And here we construct the loss function because we do, yeah, the test now is to node classification. So we have to use the same net, but use part of the node for training set and part of the node as testing. So we need a mask to separate for the loss. And yeah, then yeah, here's the next structure. So we have to use the mask to separate each. Okay, so let's go to the end. So I do some evaluation, and yeah, so there are different matrices. I mean, adjacency matrices. So in general, yeah, this one is the graph convolution, and this is a symmetry normalized adjacency matrix. It's provided by a regional stack exchange, so they are really close. And of course, I do another study, and like 1K hopping, K equal to 1 expansion, and K equal to 2 expansions of the spectrum convolution, and you can see the accuracy indeed increased. And let me see. Okay, yes, yeah. So the highest one I can reach is the accuracy is about 0.8. So the expansion method get better accuracy than just convolution, graph convolution. But I don't have much time to do more details, but hopefully that help to understand. Yeah.